So you may remember in one of the first videos, we were talking about energy, and we gave an analogy that Feynman gave, talking about his child, talking about a little boy who kept hiding blocks from his mom. And what we said was every time there was a block hidden, the mother would find it, or she would deduce ways to find out if it was there, and that the number of blocks always stayed the same. And we said that was analogous to energy. Well, now we're finally ready to talk about energy. So let's see how these are related. So let's say we have two particles. Say we have a proton that's positively charged and an electron that's negatively charged. Okay? So I think most of us have had enough, chemistry in high school and college that we know that these are going to be attracted to one another. And so if they're initially at rest, it's sometime later, they're going to be a little bit closer, and the proton's going to have some velocity toward the electron, and the electron is going to be moving toward the proton. And then sometime later, eventually we'd get to a point where, if we ignore the actual physics of what would really happen, we can say that these two particles would come head to head, they can collide, and then afterwards they would go back off in opposite directions because there was just a collision between the particles. Now again, physically this isn't exactly the way it would happen. The processes that talk about what would happen as they actually get really close to one another are well beyond the scope of this class. But for this analogy, it makes sense. If we think of the proton as a little ball and the electron as a little ball, and they just come toward each other, they collide, and they go back off in opposite directions. Okay, so how is this related to energy? Well, the energy of the system is constant. Okay, this is the principle of the conservation of energy. So as long as we don't add any energy to the system, if we just draw a box around this and say we're not going to let anything in or out, then the energy in this box is always going to stay the same. It's never going to change. Okay, but it does change forms. So for example, initially the particles aren't moving at all. So we say that all their energy is potential. So we have potential energy. But then once they start moving, okay, as we'll see, the potential energy is related to the distance between them. So as they get closer together, there's actually less potential energy. And so that energy has to go somewhere if energy is a constant. And so in this case, that's going into kinetic energy. So for the system, if we look at it at each step, at any one step, we say that the energy is equal to the kinetic energy of the proton plus the kinetic energy of the electron plus the potential energy as a function of the distance between the two of them, of the proton and the electron. And so what we'll see in this set of lectures is how we can calculate these changes between energy. And there's many different forms of potential energy. You have rotational energy, you have spring energy, you have vibrational energy, you have there's a number of different potential energies, and there's even a lot of different kinetic energies. You have energy that's due to rotation, so you have rotational energy. You have this kind of kinetic energy, which is translational kinetic energy. You even have thermal energy, and heat is almost a kind of kinetic energy. It's almost a combination of kinetic and potential energy. So there's a lot of different forms of energy. But this works even if you have a system that has a lot of different particles. So now imagine we have a system that has just a lot of electrons and a lot of protons, and they're all in there, and they're bumping off of each other, and each one of them has some different velocity, but every time they bump into each other, their velocities are changing. Their distances from each other are changing all the time. And so both their kinetic and potential energies are constantly changing. So it's almost kind of remarkable that even if we do this, if we add up the kinetic energy of proton 1 plus the kinetic energy of proton 2 plus all the other protons plus the kinetic energy of electron 1, kinetic energy of electron 2, and all the other electrons, and then the potential energies between them, right? So we'd have potential energy between proton 1 and proton 2, as a function of their distance. You'd have a potential energy proton 1 and electron 1 as a function of their distance, and the same for every other particle. And then if we add up all of those energies together, we still get the same constant that we started with at the very beginning. And so that's really kind of a remarkable symmetry of nature that leads to this. That's that if you get much deeper into physics, it becomes very, very interesting. But for our purposes for this class, the most important thing to know is just energy is constant as long as there's nothing added in. Now what we're going to see in the next unit, so that's not in this unit that's going to be on this exam, but on the next unit, you can actually come and have energy come in from the outside the system. And so you can have outside energy affect what's going on inside the system. And so that's going to change things slightly. So for this unit, we're just going to focus on what if we just kind of draw a box around our system. We don't let anything in or out. So for our purposes, energy is completely and totally conserved.